Welcome to the second video on sample presentation of statistical test results in RStudio. In this video, I'm going to look at the independent samples and look at, I suppose, the independent t-test and the Mann-Whitney U-test. And again, I would have mentioned this in the part 1 video that the purpose of these set of videos is more just about how to maybe look at collating the results as opposed to the actual process explaining all the steps along the way. So I'll still work through all the steps that checking the data for normality, homogeneity of variance, do the test, do the effect size calculations, but won't necessarily be explaining what's happening behind the scenes for all those tests. The purpose for the video is more how do we compile all the information that we have at the very end, and I suppose it's the sample, and you might decide that when you're looking at summarizing your own results that you might look for more information or less information, but maybe the points that are mentioned here in this video might be just a starting point, okay, for you. The data that we're going to look at, so this is, we would have looked at this data in the first video, so part 1, and this would have been derived in a previous video up on YouTube, and there's information on it over here. So we're looking at comparing, I suppose, two independent groups. So the obvious case here for this data set that we actually have, which is basically a randomly assigned values and so on like that, would be looking at the males against females. So they would be our independent groups, or between subjects factors, another way of calling it. And we're going to just see, is there a difference in triglyceride measurements at baseline between male and female? Okay, and that's just more, I suppose, again, this is just an illustration of how do we summarize the results at the very end. So we obviously need data to practice on, and I think for the purposes of the video, that will be should work out okay. All right, so we'll go to our script. So in part 1, I would have mentioned already all the packages that would be required for this. So if you haven't seen part 1, it might be a help to kind of, I suppose, explaining, I suppose, the background to these videos. And for part 2, what we're focusing on are the independent samples. So our first step here is just to kind of select our data. So I'm going to filter it based on baseline because I just want to focus on the baseline measurements, exclude month 1, 2 months, 3 months, 4 months, and then select the data, just condense it a small bit, that'll just be participant ID, the gender, and then the baseline measurement. So just to see what that actually is here. So this is just where I'm just using the dplyr package and the filter and select functions, and then this is where then we have the 16 participants at baseline, males against females. So in this case here we have 7 females and we have 9 males, so checking homogeneity variance will be important, and obviously checking the normality and so on. Okay, so I'll do those checks but not kind of dwell too much on them. I always feel that when even though I'm kind of quickly going through the steps, it's always nice having a picture in your mind to look, what does the data actually represent. I would have said in previous videos that when I'm drawing plots using ggplot, I generally do it in 2 steps. The first step is just to draw the plot, and then the second step is kind of to refine the axes, the text sizes, and so on like that. So if I do that here, this is what we end up with. I didn't explicitly say set gender as a factor, so even though it will be, I suppose, so in that case then the levels to the factor female and male, it automatically picks female being the first level, mainly down to alphabetical order. If you wanted male to be your first level, then you'd explicitly say that in the factor, and we'll actually see that for this and the example that we have in the part 3 video when we're looking at time. But anyway, for the purposes of this, what we can see here is that there appears to be a difference in, I suppose, triglyceride measurements at baseline, males against females. That would have seemed to be the case. But let's go off and let's do the stats then to determine if that's actually the case, okay? And again, the focus will be more on presenting the results. So the first thing we want to just check for, I suppose, and I'm quickly going through it, but mainly we'll be just looking at the normality of the data. So looking at the mean, the median, the skewness, and then actually doing the test of normality. In this kind of script that you see here that I've highlighted is script that I would have used in previous videos as well, and kind of explained in a bit more detail in previous videos. So you might want to reference to go back to that if any of this is not clear. So what we can see here for our 2 independent groups, so the males and females, which is ultimately between subjects factors, what we have is gender. We can see that for the females, there is a difference in the triglyceride measurements. Now, the unit for the triglyceride measurements is milligrams per deciliter. We can see that there is a difference between the mean and the median, but I mean, it's that they're supposed to be roughly the same. Now, what roughly the same means, it varies depending on the context. We can see with the skewness for the females, it's between -1 and 1, and then we have our test of normality using the Shapiro-Wilk test, and then we can see with the males. Okay, so ultimately our data would appear to be normally distributed. We'll do a homogeneity of variance test because our sample sizes are not the same for males and females, so it's important to check the homogeneity of variance. What we can see here is when it comes to the homogeneity of variance, the p-value we actually have here is greater than 0.05, so that would mean equal variances that are assumed. You can just see here R is giving me a small bit of a warning that I haven't explicitly called gender a factor, and we get away with it here, and I didn't just do it in this case, I suppose you'd say nearly down to laziness, but I mean, if there's no, I should have by right actually done it. Okay, so look, we'll move on. So we're satisfying the condition of homogeneity variance and normality, so then that means we should be confident to go off and running a t-test. So when we do a t-test, and more so an independent t-test, we're looking at baseline with respect to gender. There's no requirement to state that the confidence level is 0.95, which means you're working from a 5% level of significance, but I find it just useful because it just kind of reminds me, oh, that's my level of significance. You say that your paired is equal to false, and then in this case here, we're saying that the variance equals is actually true. Okay, so variances are actually equal, and that's down to the homogeneity of variance. So when we run that off, the result here, I'm going to call it 2.1, so res 2.1. And we see that the output that we get here is very similar to the output that we would have got from when we did the one sample t-test in the first video. What we're mainly interested in here is we want to kind of extract this, which is the p-value that we have for the difference. So ultimately here it tells us that there's no difference, or the difference that we are observing in our box plot is statistically insignificant. That's what we're seeing here. Here we have a confidence interval of the differences, and what we can see here is obviously the confidence interval contains 0, which suggests that no difference exists. And then down here we have the males and females measurement, a mean measurement at baseline. Now, so what we want to kind of extract from this here is we want to extract the p-value, and we want to extract the confidence interval, and we'll want to extract, look, what is the actual difference between males and females. So we'll want to subtract these two numbers from each other when we're looking at presenting the summary statistics, okay? The other thing that can be of use at times is the effect size. To see, look, there is a difference when we're looking at the box plot. There is a difference. The t-test is telling us that the difference is statistically insignificant. But if we run off an effect size for it, we might find that the difference, even though statistically significant, maybe it could be a large difference. And this might motivate us to go off and gather more data, do a power analysis to determine what sample size do we actually require in order for the difference that we're observing to be statistically significant, and so on like that, okay? So as mentioned in the first video, I find the RStatics package quite useful here. I'm going to use Cohen's d function. When you use the Cohen's d, it tells us that the difference that we're observing here is minus 0.72. That's just down to the order of the subtraction, and we can see that it's classified as a moderate difference. So what I would have done in the part 1 video then is I just would have actually done a classification measurement here. Okay, so this is what line 151 is doing down to here. So I'm just going to, I suppose, extract the effect size calculation from that line of code that we have previous. So this is to given the effect size as a value rounded to 2 decimal places. And then in the next few lines of code here, I'm just classifying it, okay, to what output do I want to see. And so the output that I'm going to get here in this case will be that my effect size will be moderate, and then I'm backing that up with the actual Cohen's d statistic then. Okay, then so this is then where, so there are all the kind of the stepping stones, and then how do we actually want to present the results? And what I would have said in the first video is that often when I would facilitate a lot of training courses, and often in the training courses that you'd spend a lot of the time talking about the descriptive statistics, doing the descriptive statistics and figuring out how best to interpret them, and the same with the statistical inference, that sometimes there's not a lot of time spent on, look, how do we actually present the results? And I suppose that's the real driver, the real purpose to these videos is how do we present the results whereby we're not necessarily creating a table manually in Word, or we're not copy and pasting values. We're actually going to have a track record. We're going to have the data transparency for how we're generating these tables. Okay? And that's ultimately what this last section is, and that's what we're kind of the purpose for each one of these is here. So it's just where I'm going to try to create a table where I'm looking at the mean difference between the two independent groups. I'm looking at the confidence interval of the difference, the lower and the upper value, look at the p-value, which is for the independent t-test, and then look at the effect size. So this is just an example of how to present a summary statistics. You might find that you don't need the effect size, then leave out that bit. You might find that you'd like to put in the test statistic and the degrees of freedom, and you can see how I'm kind of looking at the attributes to res 2.1, which is the result from the independent t-test, how you can actually extract the degrees of freedom and the test statistic if that's that's what you're mainly interested in. For the purposes of the video and for consistency through all the examples, what I'm looking at here is I'm just looking at the mean difference. So this is where I'm looking at the result that we have. If we do a $ estimate, that will give you the mean difference for males and females. We want to subtract them, so we do group 1 minus group 2. So that's what that will give us. If I just actually run that guy off here without it rounded, just highlight it like this. Look, that's the actual difference between males and females. Okay, so it's 20 milligrams per deciliter is the difference. Is that difference statistically significant? Well, that's what we have the p-value here to 3 decimal places. Now we know that the difference that we have is statistically insignificant. It's greater than 0.05 if we're working off a 5% level of significance. We have a confidence interval of the difference, and then we have the effect size. So that's what all this information is here. And then if we put that as a table, then this is what we have. So we have the mean difference of minus 20.3, the confidence interval of the difference, the p-value, then the effect size. Now, you mightn't like the way it's all the differences are negative. You might prefer to present the differences as positive. So in that case, then when you're defining gender as a factor, you explicitly state the levels to the factor, and you put male as opposed to female first, and then the differences will all be positive then. Okay, but for the purposes of this video, I like what is here because this is basically our summary statistics for the independent t-test, and we can just write that then to an Excel file here. Write it to Excel file. I won't format it in the Excel file, but this is what we would have seen before. So this is where we're output 2.1. And this is actually what we have. Okay, so we have all the information now in a nice kind of, obviously we want to format the table, borders, shading, and all that stuff. But ultimately what we actually have now is we have script in RStudio that is looking at, I suppose, showing the track record of how we're actually generating a table that we're going to use in our paper or in our thesis or wherever the case is. Okay, so that's kind of that part. For completeness for each one of these examples, I just feel it is good to look at the non-parametric version, just so that when you're there's just, I suppose, subtle differences how you handle the non-parametric version and how you handle the parametric version as in the test. So just want to quickly go through those steps. Mainly just down to, look, when you were working with your own data, you might find that your data is not normally distributed and you're going to apply a non-parametric test. Or equally, you might say, look, you do a data transformation and do a parametric test. Look, that's up to you to decide if that's what you want. But if I suppose for the purposes of this video, I just wanted to show, look, how to present results for a parametric test and a non-parametric test. So the non-parametric test is, there's not a whole lot to this one. It's I definitely came from myself now as a background. I definitely came from the SPSS school, I suppose, of statistics at the start. And when if your data was normally distributed, you do an independent t-test if your factors were independent. So if you're doing it between subjects design, and if your measurements were not normally distributed, you did a Mann-Whitney U-test. That's how we called it. The Mann-Whitney U-test in RStudio is actually the equivalent to that is using the Wilcox test, but you explicitly state that your data is not paired. So if you state that your data is not paired, which means paired equals false, that is basically your equivalent to a Mann-Whitney U-test. Okay, and when you say paired equals true, that is your traditional Wilcoxon test. So the code that you're going to use here is the Wilcox test. This is very similar to what I would have had in the first video when we were looking at the Wilcox test for a single measurement of where we were comparing it to a population parameter. So I'm saying, but in this case here, I'm just saying paired equals false, so that's an additional part. I'm saying detailed equals true just because what that will do is this will output the confidence interval as well. Okay, if I say detailed equals false, which is actually the default, so you don't need to say it, it just won't give you the confidence interval, that's all. So if I run that off first, so this is using the RStatics package. You can see that you have the median difference here on the far left. Then you have your groups, the sample sizes, whereas the p-value here, the p-value is greater than 0.05, so again, statistically insignificant. Then you have confidence for lower and upper values, okay? The next thing then, if you're to do something like this, and I suppose it's important maybe just to say here, this was not a requirement. The data was normally distributed and we satisfied the condition of homogeneity of variance. So the independent t-test was the right test to do. The only reason I'm doing the Mann-Whitney U is purely as an illustration. It's actually not a requirement based on the data that we have here. This is more just an illustration on the script that you would actually use. Okay. So the next thing then is, and nearly finished this part then, is just to work out the effect size. So we're going to look at the Wilcox S size. This again is from the RStatics package. What this will give back then is the effect size, the R effect size. So this is where you're looking at the classification of 0.1, 0.3, 0.5 between distinguishing between negligible, small, moderate, and large. Here I'm isolating the effect size calculation, so I try to keep the scripts very similar to the previous ones. Just I feel as a starting point, it's nice when the script doesn't change too much, so that we kind of get comfortable with the approach, and then we can start, when we're, I suppose, comfortable and confident with the approach, we can start deviating it then after that if we wish. The next step then is just classifying it as negligible, small, medium, small, moderate, or large. In this case here, where it's going to be classified as moderate if we're using the this effect size classification. Okay, so that's where we are. And then the last step then here is just actually presenting the results. In this case, instead of the mean difference, it's the median difference, because the data we're saying this is like a what-if scenario. The data we're saying is not normally distributed. We have the confidence interval of the median difference, then we have the p-value, and then the effect size. So that's where we are here. I'm going to quickly run through them, and these are the statistics that we come back with. And then I'm just going to write that then to my Excel. So if I write it to Excel, then you're going to see I have an output 2.2, and there we have it. Okay, so we have the median difference between our two independent groups, males and females, classified as minus 20 milligrams per deciliter. We have the confidence interval of the difference, which contains 0, so hence suggests that there's no difference exist. We have the p-value, which is greater than 0.05, which means the difference that we're observing is statistically insignificant. And then we have the effect size, which we're using this classification of 0.1, 0.3, 0.5. So using this classification system, the effect size that we're observing then is a moderate effect size. Okay, so look, that's where we are with this. I know now I'm quickly talking through it, but obviously I suppose that's what the beauty of these videos on YouTube is, that you can kind of pause, rewind, and so on like that. Hopefully you find this video of use. Hopefully it'll be a benefit to you. I definitely feel having a track record to how you're producing tables is very good. It's only natural that people will ask questions. It's only natural that people might be concerned that there might be, I suppose, errors in how tables are presented at times, and there's a big emphasis around open science these days. So it's just great, I would feel, if we can, to always have a track record in our statistics. I think that ultimately leads to good practice in statistical analysis, which I think is a good way to do things. Okay, so if you come back to the third video in these set of videos on sample presentation of statistical tests in RStudio, I'm going to looking at two paired measurements. Okay, so it's going to be kind of very similar process steps, but it's going to be focusing on the two paired measurements. If you find this information good, it'd be great if you liked, shared, and even subscribed to the channel. Subscribing to the channel would be a great benefit, please. And this ultimately then will allow you, I suppose, you'll get notifications when new videos are uploaded, and there will be new videos. This is going to be a long project that I have that I'm working on. Okay, but for the moment, that would be it, and hope you come back for the third video. Thanks, all the best.